All right, so if you looked at all the previous examples, if you looked at the sequence, your A sub n, and you looked at them, you go back, look at them all right now, take some time, go back, and if you were to just take the limit of those sequence functions, you notice the limit's going to be 0. So if you have to find an infinite series, it's going to be convergent when the limit of that series is equal to 0. And if it's going to be geometric or telescoping, we can go find that sum. Now, however, the converse is not true in general. So if you switch the statement around, that means switch what we call an if-then statement. If the hypothesis, then the conclusion. If you put the conclusion first, if the limit as n approaches infinity of a sub n is equal to 0, we can't conclude that the summation is going to converge. So this theorem here is going to lead us to a good test for divergence. So theorem 7, if you will, the test for divergence. If a limit as n approaches infinity of a sub n does not exist, or if the limit of a sub n is not equal to 0, then the series is divergent. So here we know that we're convergent if our limit goes to 0. Okay, so if we take the limit now and show anything else but a 0, it doesn't exist or it doesn't equal 0, then we know it's going to be divergent and we don't have to try to find its sum. So if we look at previous examples, here we know that this was a divergent series. So again, if you just take the sequence, take its limit, and its limit is equal to infinity, which means it doesn't not exist, it's divergent. It's going to diverge. Here we had that geometric sequence. If you take the limit of this right away, it goes to 0. Okay, it may converge or it may not converge or diverge. We don't know. We are going to have to go and test it out. So here, example 10. Let's take the summation of 1 to infinity. So we're looking for an infinite sum, an infinite series, 4n plus 1 over 3n minus 1. Let's take its limit. The limit as n goes to infinity of 4n plus 1 over 3n minus 1. Okay, so if I go ahead and I divide all the terms by n, this becomes 4 plus 1 over n. This becomes 3 over minus 1 over n. This becomes 0, and I have 4 over 3 left. 4/3 does not equal 0. Therefore, I know this diverges. Okay, next, theorem 8. These are all of your properties of summations, where c is a constant. So if you have a scalar being multiplied to your sequence, again, you can factor it to the front. If you are adding two sequence functions together, you can write them as two summations. Same thing as if you're subtracting the two sequence functions, you can write the summations as subtraction. That way we can look at those limits individually. So for example 11, we need to separate this. Let's write two terms on the top, one factor in the bottom. Let's write it as two fractions, 1 over 3 to the n plus 2 to the n over 3 to the n. Separate them into two separate summations. These both converge. These are both geometric. 1/3 is less than 1, 2/3 is less than 1. So I know, taking the limit, this is 0, this is 0. They're not, that would be, okay, they're not going to converge or diverge, but then checking that they're geometric, they both converge. So I have to go use something else. So now I can find the infinite sum. So first term, okay, we'll have to put in a 1. 1/3 to the first power is 1/3 over 1 minus the r, 1/3. So that's going to multiply the top and the bottom by the 3's, gives you 1 over 3 minus 1, or 1/2. Over here, put a 1 in for n. First term is 2/3. 1 minus 2/3 is going to give me 1/3, or 2/3 divided by 1/3. You can multiply by its reciprocal and get a 2, or multiply top and bottom by 3 to get 2 over 3 minus 2, which is a 2. 1/2 plus 2 is 5/2. So there's my infinite sum. So again, as I mentioned earlier, divergence test. This limit goes to 0. This limit goes to 0. Therefore, I know they're not going to diverge. But then again, I'm not sure if they're going to converge either unless I check, oh, notice they're geometric. Then yes, they're both going to converge. So I have to do something else to justify if they're going to converge. And the next thing I want to point out is that remember, you don't always have to start at n equals 1. So if you have this series here, and this series was shown to converge, all right, we can prove, okay, if I make it n equals 1, add in the first 3 terms. If you add in the first 3 terms, if this converges, then so will the sum of these two together will also converge. So if terms are missing, it's not going to affect its convergence or divergence. All right, so keep that in mind. Oops, went backwards too far. Sound good? All right, so that wraps up our 9.2.